Today I will be melting some bismuth. Bismuth is located at the far right of the periodic table, next to lead and polonium. Meaning it shares physical and chemical properties with antimony and other elements in this group. The isotope I'm melting right now, Bismuth 209, is the only naturally occurring isotope of bismuth. It has 83 protons and 126 neutrons, giving it a total of 209 nucleons. Bismuth was long thought to be stable until 2003, when scientists discovered that it is radioactive, though with an exceptionally long half-life estimated at 2.01 times 10 to the 19 years, practically stable on human timescales. Bismuth 209 undergoes alpha decay to thallium-205 with a Q value of approximately 3.137 MeV. Alpha decay occurs in nuclei, usually with the proton number above 82, where the Coulomb repulsion between protons overcomes the strong nuclear force. When nuclei above the proton number of 82 generally become less stable, bismuth is almost doubly magic. 83 is just above the magic number 82, and 126 itself is a magic number. Magic numbers correspond to closed shells of protons and neutrons, which confer extra stability. However, having magic numbers doesn't automatically make a nucleus stable. For example, calcium-48, which is doubly magic, has an extremely long half-life and decays via double beta decay because single beta decay is forbidden. A positive Q value indicates that alpha decay is energetically allowed under the rules of quantum mechanics and energy conservation. If the Q value were negative, the decay would not occur because extra energy would be required. Using the HF equation to calculate the total energy of all electrons, bismuth electron system has about 500,000 keV of energy. Despite being near highly toxic elements like thallium, lead, mercury, and polonium, bismuth itself is extremely non-toxic. Its stability is due in part to relativistic effects, which contract the 6s orbitals and favor the +3 oxidation state. Bismuth is relatively unreactive, insoluble, and most of its salts are also insoluble. Because it cannot mimic essential ions in the body, it is harmless. Alpha particles released by bismuth cannot penetrate skin or paper, though they do ionize the air by removing electrons from atoms and creating radicals. In a 1 kilogram sample, bismuth rarely releases 1 alpha particle per minute. For comparison, a banana containing potassium-40 is far more radioactive than 1 kilogram of bismuth. Bismuth has a relatively low melting point for a metal, around 271 degrees Celsius, and a density of 9.78 grams per centimeter cubed. This is because the metallic bonding is relatively weak, allowing the bonds to break more easily. Bismuth is also one of the most diamagnetic metals, meaning it is slightly repelled by a magnetic field. You may notice a rainbow-colored surface on bismuth. This is bismuth oxide, typically only a few nanometers thick. This oxide layer protects the metal from further reactions, though bismuth itself is relatively inert. Under specific conditions, bismuth forms hopper-shaped crystals, where atoms arrange themselves into geometric, city-like structures due to the way metallic and covalent bonding interacts during solidification. Bismuth is also used in medicine, such as Pepto-Bismol, where the active ingredient, bismuth subsalicylate, coats the stomach and digestive system, helping to reduce irritation and discomfort. In summary, bismuth is a fascinating and unique element